Businesses usually want to take actions that have hopefully the effects they want to bring about occur. And so in my mind, that's all about understanding the problem from a causal point of view. At Spotify, we've been having a lot of kind of success recently with like the types of projects we're working on and like the areas in which we're applying causal inference beyond just what was the impact of that product launch or that new feature or whatever to really drive actions and so forth. So a lot of these are kind of at a late stage now. So we're, final testing and so forth. And so I'm really hoping that they see the light of day where I can talk about them quite a lot publicly.
In one of your papers, earlier papers, you worked at the intersection of quantum physics and causality. And your work was related to the Reichenbach's principle. Can you tell us a little bit more about this work?
Hey, Causal Bandits. Welcome to the second season of the Causal Bandits podcast, the best podcast on causality and AI on the internet.
As a child, he loved Lego. He chose to study quantum physics to keep his joy of building alive. His research has been published in Nature journals, accepted at top machine learning conferences, and called a breakthrough by popular outlets. In his free time, he writes for new scientists and helps his students apply causal methods in new fields. Ladies and gentlemen, Dr. Kieran, Gilligan-Lee. Let me pass it to your host, Alex Molak.
Welcome to the podcast, Kieran. It's great to have you here.
Thanks very much, Alex.
It's a new thing for me, a new thing for you, I suppose, as well. It's the first online podcast and the first live podcast. So there are two things that are very, very new today. I wanted to start with a very, very general question. You came from background in quantum physics, and then gradually you moved towards working with causal models. And today you're the head of the Advanced Causal Inference Lab at Spotify. What types of problems can Causal AI help us with in companies like Spotify? Causal AI or causal modeling more broadly?
Yeah, it's a great question. So in my view, most questions we're interested in from a business point of view, right? Businesses usually want to take actions that have hopefully the effects they want to bring about occur. And so in my mind, that's all about understanding the problem from a causal point of view, figuring out, okay, if I take this action, what effect will it cause? Usually in most kind of big tech companies, we use lots of data to try and, train models to understand the best things to kind of do. That's, suggested by our previous kind of data and so forth. But all this data usually is kind of collected in some sort of observational sense. So, there's selection biases going on. There's other biases. There's, reasons why users do certain actions on, various platforms and in big tech companies and so forth. And so if we want to answer these kind of business questions, which are, from my point of view, fundamentally causal questions about cause and effect, then we need to use causal inference to really take this observational and bias data, remove those biases in the right way, and then use it to kind of make these good, actionable decisions for, various business outcomes. So, it's a very vague, high-level answer. We can go into specifics in a while, but every time you want to understand what effect an action will have or a decision will have on future business outcomes, you need to use causal inference.
One of the methods that I saw in more than one of your papers is synthetic control. Is there something special about this method that you find it particularly useful, especially in the context of your work at Spotify?
So it's a great kind of methodology for when a treatment has a very precise time at which it's been administered to, either a user or a population or some unit that you want to understand the effect of that intervention on that unit. So when you have this very precise nature, it happened on this exact time, on this exact day and so forth, synthetic control is great because you have a very clearly defined before treatment period and after treatment period. And in, lots of cases, Spotify, sometimes it's difficult to figure out what confounders would be the right things to do to adjust for various things. Synthetic control has a kind of nice approach in that once you can find similar looking enough units, you can use them to construct a synthetic control as long as they haven't been impacted by the treatment as well. And then this thing can then help us understand what the impact of that treatment or intervention was on the specific unit at that time. And it just turns out that a lot of kind of questions we have in big kind of tech companies are really kind of questions where an intervention happens at a fixed point in time, like a new feature is released on this day, or, a user interacts with an artist in a very fixed way on this point in time, and we want to figure out what the impact of that is on future time points and so forth. So it's a really useful methodology for that, both when we have this very fixed kind of time period at which the intervention happens and when perhaps it's difficult to figure out what this big set of confounders are that we could control. Maybe some of them are hidden from us, but we do have a set of similar enough looking units that aren't impacted by the treatment, and we can use those then to try and infer what the causal effect is.
Synthetic control is also a very intuitive method. Like every time I talk about causality to someone who is not familiar with this topic, and I talk about this method, people tend to grasp it very, very fast. And I think it's a great advantage of this method. But perhaps at the same time, it's also a disadvantage because this intuitiveness of the structure of how synthetic control works can also make us more susceptible to believing that this method gives us causal identification out of the box, which, as we know, it's not true, unfortunately. In one of your papers, you describe ways of combining synthetic control or quasi-experimental methods with the framework of DAGs, directed acyclic graphs, and then you use both to ensure that you have causal identification, and it also allows you to put a sensitivity model on top of this later on.
Yeah, so synthetic controls were originally developed by economists and so forth. And, the kind of viewpoint of the economics background is somehow slightly different than, let's say, the Peirlian SCM computer sciencey approach. Both are, conceptually very related, but there's kind of key differences in these two kind of groups of individuals. So for the synthetic controls that were kind of standardly known in the literature and so forth, no one, as far as I could see by the time I first, came about to learn about synthetic controls, nobody had drawn a DAG about, what the synthetic control model kind of looks like, what the underlying graphical assumptions might be, and so forth. And I thought this to me, coming from a very, computer sciencey background, was strange. It was like the first thing I did when I heard about them was draw a DAG. It seemed to be a strange thing to do for synthetic controls because it just wasn't done in the literature up until that point. But, coming from this economics background, the assumptions that went into the model were sometimes very semi-parametric. So the underlying assumption was that, there are these linear factor models generating the time series evolution of the unit that we want to understand the impact of the treatment on, as well as all these other similar units. And when we say similar units in the economics literature, what we meant was that it's the same linear factor model, or at least so the same family of linear factor models that are influencing both the treated unit and these similar units that we're going to use to build the synthetic control and so forth. And we have to have some commitment that that underlying linear factor model is the same before the treatment as after the treatment, apart from the introduction of the treatment kind of impact itself. And so to me, this seemed like a very kind of stringent set of assumptions, and it didn't kind of lend itself, at least in my mind, very cleanly to doing things like sensitivity analysis. What happens if that assumption breaks slightly or is slightly violated? Because it's relying so stringently on the semi-parametric kind of form, it's hard to know what happens when you go outside that. And so one of the first things we did when we started thinking about them in a kind of deeper way after drawing the DAG was trying to figure out, okay, what set of assumptions will enable us to kind of show that you can identify this synthetic control, this counterfactual, that'll help us figure out what this causal effect is after the point at which it's been administered. And, we settled on a few assumptions that were non-parametric, and then proved some general theorem that kind of allowed us to show that you can get these kind of nice identifiability results from these more general principles. It's all about using ideas from kind of proximal causal inference. So here, instead of there being an underlying latent factor model, you just assume there are these underlying latents driving the evolution of all these units, the treated unit and these, donor units that will hopefully build the synthetic control. But instead of assuming further that, there's this specific parameterization of this, that they're linear factors of these kind of underlying drivers, what you do is you just say, well, these drivers are proxies for these underlying latents. We don't say specifically how they're functionally related. We just say that they're proxies. Then you can use tools from proximal causal inference. Again, here you have to make some assumptions about what it means for one variable to be a proxy of another, right? To tell you a bit of information about it, even though it's not precisely what that variable is. But once you make those assumptions, you can then derive these general identifiability results. You don't have to rely on linearity and so forth. But the cool thing about this is now that we have a really clear set of non-parametric assumptions, we can check what happens when they're violated, right? We can build some synthetic or some sensitivity analysis around figuring out, okay, well, if this assumption slightly doesn't adhere in the general data generation process we're looking at here, how wrong would we be, right? How much should we have confidence in the causal estimates that come out of this if, let's say, some of the assumptions are misspecified and to some degree at least? And so we can use these tools then to gain more confidence. And so it's this marriage of this kind of SEM Perlian approach with this econometrics idea to allow us to do kind of general sensitivity analysis and gain more confidence for these synthetic control estimates.
What are some of the ways that you build trust in your causal models?
It's a really good question because, the main thing, let's say, deep learning practitioners think when they first are introduced, let's say, to causal methods, is they're like, wow, there's so many assumptions here, right? Like, how can I really trust these results if I have to commit myself to these assumptions? And, forgetting that when they do calculations themselves, there are these inherent assumptions going on that allow them to kind of be certain that their predictions will make sense and not kind of, undergo domain shifts and various sort of things. They just aren't generally used to making these assumptions and so forth. And so they don't think about them too much. In my view, having to make these assumptions up front and think strongly about them is actually a bonus, right? It makes you really think deeply about, does the data generation process in this specific problem, does it actually seem reasonable that these assumptions are kind of, satisfied in this case, or should we really, change up the methodology that we're using to try and extract insights from this? And so generally there could be many ways in which these assumptions could be violated. Like, for instance, usually you have to control for confounders, and you're obviously limited then. You have to measure all relevant confounders, and there's no way that you can precisely know that you've captured all confounders. But there are various kind of ways in which you can gain confidence in that fact, right? You might have some domain knowledge that'll tell you, okay, well, I presumably have missed some confounders here, but from this domain, I really know that this confounder, this is probably the most important confounder, right? Like, it would seem very strange to me as an expert to think that there's another confounder out there we haven't measured that's more important than this one. So I can use how strongly that influences, my kind of methodology, my end result, to say, okay, well, if I've missed something, it'll be less important than this one. Still be important in principle, but it's still going to be less important than this. Then from that, I can set bounds on how much my effect estimate might change if I had actually measured that quantity and put it into my analysis and so forth. And then you can still make kind of claims, right? Maybe you won't be able to point identify the causal effect, right? Know exactly what it is, but you can still get some upper and lower bounds. And perhaps if those don't intersect zero, you can say, well, there is a causal effect here, right? It's non-zero. And so that's maybe enough in some cases for certain business applications. This new feature has a causal impact. It's not close to zero and so forth. So you can kind of, by understanding these assumptions and then figuring out ways in which how the violations of them lead to changes in your causal effect estimation, you can put bounds, or you can get more certain about these types of things. And to my mind, that's like a feature, not a bug of causal inference, right? Having to make this assumption forces you to think deeply, but then also forces you to say, okay, well, if they're violated, I can still get some confidence in what's going on. I'm not shooting in the dark.
That's very interesting. I think in deep learning, we often love to forget that there is a lot of assumptions underlying those models as well, right? And the main one, and probably the most heavy one, is the IID assumption that Bernard Schulkopf called the biggest lie of machine learning. I want to move a little bit towards something more practical, more applied. What are the main challenges in causal machine learning engineering versus traditional machine learning engineering?
So I guess it's, a lot of additional work needs to be done to make sure that any misspecifications of some of the variables don't lead to, big changes in the outcomes that we want to predict and so forth. And sometimes one might naively want to add all the potential confounding variables one can think of, right? It could be in, applications of Spotify, there could be thousands of potential confounders, hundreds of potential confounders. And you might naively think, okay, I should just condition on everything. I should control for as many possible things as possible. But before you go to that engineering step, right, plugging things into different estimators and, all this kind of stuff, you really have to kind of think, okay, are these things actual confounders? There are a lot of results in the literature that kind of show us that, naively controlling for lots of things actually doesn't end up identifying the correct causal effect. It actually leads to worse estimates, right? It's because some of those things may not be confounders. They might be, colliders between the treatment and the outcome and so forth. And like, you have to have this prior step before you go about and do all this engineering. You really think deeply about, okay, what's the DAG here? What are confounders? Should that thing be in my adjustment set and so forth? And then once you understand that, you can kind of think further, okay, how noisy is my data? What does it kind of look like? What are the variances and so forth? And that might guide you to specific methodology. Maybe you want to do like double machine learning or, various other approaches here. Things like standard bread and butter, like inverse propensity weighting and so forth. There's many situations where, given the type of data you're looking at, that might not be the right thing, right? If the action space you're looking at the confounder set have very large variance in their values, some are very small, some are very big, it can be difficult to kind of get reasonable control on the variance of some of your causal effect estimates and so forth. So you have to think a bit more deeply than just plugging everything into a black box and then trusting what the outcome is. You have to think before you even do that. And then when you look at the data, you think about, okay, what methodology should I be using here to really get confidence in the outcome, but also get as much out of the specific data I have as possible. So it's more about the conceptual framework that goes on before and even after the kind of application of these methodologies or this engineering feat.
Before you moved to Spotify, you worked at a startup in healthcare. What were some of the results that you were able to get there using causal methods?
That was a really cool role that I was involved in there, with a lot of kind of great scientists at that specific startup. So I moved to that startup directly from being in academia, and I was working on causal inference at the time, but applying it to a different domain. And I really thought the more I learned about causal inference, the more I thought, oh, this is really kind of powerful, right? It feels like this could be really practical and could help, make better decisions in various kind of fields and so forth. And so I was, found this job at this healthcare startup where we're doing research around trying to help kind of automate the kind of medical triage process, right? So help patients when they come in, they'll interact with some form of chatbot that will extract their symptoms, risk factors, and so forth. And then we'll try and triage them. So figure out what disease is underlying their symptoms and then say, okay, well, maybe you need to go to a GP, maybe just go to a pharmacist, or maybe you need to go to the emergency room right away. And so in this kind of situation, it's really critical to, have really trustworthy methods making these recommendations, right? Because you don't want to say the wrong thing to a kind of patient. And the way in which, the startup was working on this problem at the time was they were using what's called a disease model. So you can think of it as like a big probabilistic graphical model. It has three different types of nodes. So one is like your risk factors, the next is the diseases, and then the last one is the symptoms that a patient is displaying and so forth. And they had this that was constructed by, medical professionals, epidemiologists that input the direction of the arrows and all this kind of stuff. But also we had, conditional distributions between all these links in this big probabilistic graphical model. So we knew, conditioned on this disease, we knew how likely certain symptoms were and so forth. The way to do diagnosis using such a disease model, standard approach goes back to the mid-80s. And the basic idea was to say, okay, given I've observed certain symptoms, I want to figure out what disease has the highest likelihood under this evidence, or the highest posterior under this evidence, which is to say, what disease is most likely given the evidence. And so for anyone who's ever heard of the adage, correlation is not causation, you might start to get a little bit worried now, because, if you're looking at diseases that are correlated with symptoms, maybe that's not the right thing. Doctors really try and find the disease that's causing symptoms. That way, in which if they treat the disease, then they'll know they'll reduce the symptoms, or at least that's the hope. And we kind of started looking into this a little bit, guided by this intuition. And we found certain situations where this correlation approach was the complete wrong thing to do. So one kind of clear example we found was, if a patient came in with tightness in their chest and kind of chest pain, then the kind of disease model was outputting the highest likelihood disease being type 2 diabetes. And this is strange, right? Because if you ask a medical professional, they'd say type 2 diabetes does not cause chest pain. When you actually even looked at the graphical structure of the model underlying that, there was no causal link between type 2 diabetes and chest pain. So it was the wrong thing to do from a doctor's point of view, but yet the model was outputting this. And so what was going on under the hood was that, if you had chest pain, with some probability you belong to the part of the population that's overweight. And again, if you belong to that population, with some probability you have some chance of developing type 2 diabetes. So there's this association between type 2 diabetes and chest pain via this kind of confounder of being overweight and so forth. So there it's this kind of classic case where there's a strong correlation, but there's no causal link. And so what we ended up doing was reframing this diagnosis problem as a counterfactual reasoning task. So this is a real kind of Pearlian approach, where we kind of asked, okay, given the symptoms are present, so it's factual evidence that I've observed, I want to ask, counter to that fact, what would happen to those symptoms if I cured a specific disease, if I intervened on a disease and was able to turn it off in this model? And it turned out that was a much better thing to do when we compared the outcomes that came out of this approach to the kind of standard Bayesian inference approach based on correlations. and compared it to 44 doctors, we found that the counterfactual approach was as good as the top 25% of doctors, whereas the correlation approach is only as good as the top 50% of doctors. We doubled the accuracy by just going down this causal inference point of view. And what's important to note here is like the disease model itself didn't change. It was the exact same underlying probabilistic graphical model, the same parameters. We were just asking that model a different question. And so to me, that really illustrated the power of causal inference, and that it kind of showed that using the standard correlational approach was not the right thing to do, but you got a big improvement by using this kind of causal approach, which was kind of cool. And it was nice that it was in this critical area like healthcare, where you could show that causal inference was, quite important for this, and important in the sense of making a prediction rather than just, let's say, okay, I have my data set. I want to figure out how to quantify the effect of a given treatment and so forth, or what's the impact of policy. Causal inference can help you do more. It can help you predict or kind of infer what the impact might be in the future as well. So I thought that was kind of cool, coming from academia into this kind of industrial world.
What is the most surprising thing you learned from applying causal modeling in industry?
So there's a few interesting things. I guess the first is when you first hear about there can be confounding bias, and you need to control for it to kind of reduce, raw correlations between variables to check, okay, if after I control for this, how much correlation is left over, right? And that's meant to be the causal effect if I've control for all confounders, given various additional assumptions and so forth. But if you had a range of treatments or a range of actions, let's say, that you could take, and you first looked at the correlation between these treatments or these actions on the outcome you want to move, right? Perhaps it's a marketing campaign in a big kind of company. Perhaps it's a specific drug in a medical context or things like this, and you have many options. You might think, because I'm controlling for the same confounders in all cases, that even though the correlations aren't the right way to think about the impact, the relative orderings between all these different actions, all these different treatments might persist even after we control for confounding. So you might think, okay, well, the one that has the highest correlation, as long as there's still some association after I've controlled for things, that's the one that's going to have the highest causal impact, even though I can't know what that causal impact would be just looking at correlations. Turns out that in many cases, this is completely wrong. The orderings of things can absolutely flip. Things that have reasonably small correlations can have bigger causal effects than treatments that have big correlations and so forth. And so you really have to, adjust your intuition thinking about these problems in this statistical way to really think about it in this causal way. And, controlling for confounders can be very different for different treatments. And that's a kind of big thing. So that was kind of a surprising thing to me, because a priori it wasn't absolutely clear that would have been the case. Perhaps it's good enough to select the best treatment by just looking at the correlations and so forth, because you'd think the relative orderings would be preserved under controlling for confounding. But it turns out in practice, this is completely wrong.
That's a very interesting point, especially that the strength of correlation and its persistent over time are two criteria that are part of the Bradford-Hill criteria for discovering causation, right? So if we take them in isolation, it's so easy to fall for this trap. And this reminds me about this website from Tyler Vigen or Vigen, I don't know, who finds surprising correlations between different time series, like a number of drownings and movies with Nicolas Cage and so on and so on. So sometimes I use one of those examples about non-commercial space launches and PhDs in sociology awarded in the US. And I show people that correlation there is pretty strong and it's consistent over a period of 12 years. Although it seems intuitively, not connected, those two different events. This consistency over time makes some people think if maybe they are related.
When you try to think about it a bit deeper, realize in that specific example, there's probably only like 12 data points, right? One per year.
Yeah.
Right? So if we want to think about what a correlation is, we probably need more than 12 data points to be certain a kind of statistical association persists, So you can get tricked in this way by looking at these things. I remember looking at that website a while ago. One of my favorite ones was there's a strong correlation between the height of tides in Venice and the price of bread in London. So it feels, true, like there's no connection. There should be no connection between these two things. But when you kind of think about it, right, the whole of science is kind of based on this idea that there should be some underlying explanation to a correlation, right? As long as it persists in a certain level over time and so forth. It's not just like a fluctuation and so forth. And so there was this guy called Reichenbach, who was this philosopher who kind of formalized this kind of principle of two things are correlated, then there should be an explanation for that fact, right? So either there should exist a common cause in their mutual past that explains this association. So in the case of, tides and in Venice and the price of bread in London, it could be that actually The height of tides tells us when shipments from other countries come in to England. High tides mean the ships come in and then bread is delivered, so supply is high and demand is maybe low at that point, and so that sets the price. And then that also is correlated with the height of tides in Venice, right? Because they could be, geographically reasonably close and so forth. So that could be one explanation. Or it could be the fact that, similar to that example you gave, right, that actually the data points we have to witness this specific association are actually reasonably small. And so it could just be a random statistical fluctuation, and we just so happen to look at it at that point. And in that case, like naively, you might think, well, how can I represent that as a DAG, right? Well, as a common cause, I can understand, right? There's a thing in the past that has two arrows into these two outcomes, and by conditioning on that, I can explain away the correlations between these two outcomes. Whereas in this case of having a small number of data points, it feels more difficult. But if you think about it a bit more, you can kind of think that, okay, well, it's the way in which I'm observing these two variables at that specific point in time. And so the data points that I'm getting to kind of, witness this correlation are both, it's almost like a collider between these two things. Both are telling us at this point in time what that data set is. And so conditioning on that specific data set induces this correlation, or can induce this correlation between these two things. But in that sense, the specific data set itself is the explanation, right? It's the fact that it's only over a small time period. And had I looked at a longer time period, maybe it would vanish. Maybe if I zoomed in a bit and looked at, minute by minute correlations or minute by minute data points, maybe it would go away and so forth. So it's really tricky to see correlations. We're intuitively, as humans, the kind of designed almost to try and look for an explanation. And I think that website is there to show us that that's the wrong thing to do. But I think it just shows us how hard it is to do that. But the whole, enterprise of science is founded on that idea that if there's correlation, we need to explain it somehow, or show that it's not a correlation by looking, over longer periods of time.
Yeah, that's very interesting what you said, that maybe if we change the time scale, we would not see the correlation there, right? Or at least not as strong. So this reminds me of my conversation with Naftali Weinberger, who devoted a significant amount of his time to studying scale-specific causal effects, showing that the level of abstraction that we pick for our problem for causal variables can matter very, very significantly. You also mentioned the Reichenbach's principle, and I'm really glad you brought this up, because in one of your papers, earlier papers, you worked at the intersection of quantum physics and causality. And your work was related to the Reichenbach's principle. Can you tell us a little bit more about this work?
Yeah, I mean, it was a lot of fun doing this project back in the day. It was one of the first projects that I did in kind of causal inference in a way. So it kind of got me into the kind of swing of things. It's where I got the bug for, thinking about things in this causal way. But the kind of basic idea behind that, the inspiration for that paper, kind of came from two areas. One of which is, in some of Pearl's early work, he used this causal modeling framework, DAGs and so forth, to, explain apparent statistical paradoxes in a more kind of intuitive way. So, Simpson's paradox, Lord's paradox, and so forth. So in those situations, it turned out once you drew the DAG and reasoned correctly using the DAG, rather than just looking at statistical associations, things that were seeming paradoxes at the time, right? Things can be associated in one way, whereas when I condition on certain subsets of the data, that association can completely flip, and which one is the right one and so forth. But when you think about it from a causal point of view, this paradox is resolved in a kind of clean way, and we can understand what's actually going on. And, in quantum physics, there's a lot of chat about things that are apparent statistical paradoxes, like, Schrodinger's cat, spooky action at a distance, all these things that you read a popular science book and they seem fanciful and crazy and they don't mesh with our everyday understanding of the world. We kind of wondered whether, by placing some of these phenomena on firm causal footing, the way Pearl did, with Simpson's paradox and so forth, we could understand them at a deeper level, and perhaps some of these paradoxes would be resolved a little bit. One of the kind of biggest ones that we kind of had in mind when we started out this work was this thing called Bell's theorem. So John Bell was this Irish physicist. He did a lot of work in the foundations of quantum mechanics, as well as high energy physics and so forth. But one of his most kind of highly cited and read papers is kind of a commentary on an earlier paper by Einstein and his collaborators Podolsky and Rosen, where they kind of introduced this kind of notion of spooky action at a distance, where you can have two physical systems that are very, very far apart. And when you kind of measure or intervene or do something to one of them, all of a sudden the other one can respond or you can learn information about this other one, even though it's very, very, very far away. So this seemed kind of counter to, basic principles of physics, right? Information can't travel faster than the speed of light, but all of a sudden I can learn something about this physical system that's very, very far away from me just by looking at this one here. So it seems paradoxical. But Bell came along and Bell said, well, maybe it's not too paradoxical when you kind of zoom out. Like, here's a simple example that you can have the exact same phenomena happen. I don't even have to talk about quantum kind of physics to kind of get to there. Imagine having like two boxes. I take a pair of gloves, a left-handed and a right-handed. In one of the boxes, I put the left-handed one, and one of the boxes, I put the right-handed one. I give them to my two friends who are going on airplanes to different parts of the world. When one of them opens the box and they find it's the right-handed glove, they know instantly that the other friend has the left-handed glove. So I can learn something about that other box or the contents of that box, even though it could be on the other side of the world. And I haven't done any kind of physical interaction with it. I've just given this one friend this one box and so forth. And so maybe this kind of EPR, Einstein-Podolsky-Rosen paradox is just exactly that, right? The reason these two things have this property is because I prepared them together. I'm the common cause, the way in which I, put the gloves into the boxes and so forth. And so by, explaining that association, I can do it by just saying, well, I constructed it precisely in the way to have these associations or have these connections. But Bell showed that actually you can't do that for the case of quantum correlations, actually going down this causal explanatory route, this idea based on Reichenbach's principle, these correlations have to have an explanation. Turned out if that explanation was a classical object, right, was the descriptions of how these systems were prepared, let's say, then that it's not enough to explain it. You can show that the quantum correlations actually, when you stipulate that that's the DAG, the correlations between them can violate, constraints on what that DAG said about that joint distribution and so forth. So you just can't explain it that way. So it seems like a paradox. And so we hope that, understanding things from a causal point of view could help with this, because the main assumption of Bell's theorem was that common cause had to be a classical object, classical random variable. But, if you said, oh, it's just a quantum variable, it's a quantum system, that's the common cause. And if I do that, it seems intuitive that would explain what's going on. I prepare these two systems together in the same lab. I send them both to different parts of the world. And the reason they're associated is because of the way I prepared them in this quantum kind of way and so forth. But we didn't know how to use the language of causality in this kind of quantum setup, right? We didn't know how to say, well, what does it mean for two variables to be associated via a quantum variable and so forth. And so that was the starting point for the paper. And we did a lot of work around how do you formalize the idea of a quantum causal model? How do you replace objects like the conditional distributions and standard causal models and the deterministic functions underlying them with relevant quantum objects? And how do you justify that association is the right way to do it and so forth? And then once we have that, you can start to kind of play with things like, how do I use this formalism to do things like, if I have a big network, what happens if I intervene here and what are the influences and all this kind of stuff. So yeah, it was a fun project to kind of get into the frame of this causal inference framework.
In this paper, we also talk about quantum causal models, if I'm not mistaken. What's the difference between quantum and structural causal models? And is there a smooth transition between those two formalisms? So when we think about quantum effects, they are specific to the quantum level and we don't observe them in the macro scale. So I was wondering if, based on your work, you could tell us if we know how to make a transition from the quantum level, from a quantum causal model to a structural causal model.
Yeah, it's a good question. It kind of comes down to, what are the actual mathematical objects in the quantum case that are analogs of, these objects in the standard SEM case with classical random variables. So in the SEM case, the SEM is defined by both the structure of the graph as well as the kind of deterministic functions underlying that. And there's some variables that are observed and some variables that are hidden and so forth. And the deterministic functions plus our hidden variables, or variables that I'm uncertain about and have a prior over them, are what generate the conditional distributions between different nodes and so forth. Right? So just because I lack knowledge about some of these hidden variables, I don't know exactly what this deterministic function is, but I know there is some deterministic function mapping one variable to another. And it's because I don't know this other variable, and this is what kind of leads to this kind of lack of knowledge and so forth. And so in the quantum case, we need to find analogs of both the deterministic functions and these conditional distributions that arise from them by just not being aware of certain parts of the system and so forth. And so quantumly, even though we hear in the popular media that, there's this inherent randomness in quantum physics and so forth, there is an analog of deterministic operations. It's called a unitary map. But the reason why it kind of gives rise to this stochastic evolution of quantum systems is in a lot of cases, we don't know about the environment. We don't know what's going on. Like we could have a very um, delicate physical molecule that we're trying to put into a superposition, and it can stay that way until something in the environment bounces off it or it hits it or whatever, or information is lost from the system to the environment. But if we just knew how to describe the entire environment, that would become deterministic again, right? It wouldn't be this inherent uncertainty. And so you can show, not by just saying, okay, well, a unitary map is the direct analog of a deterministic map. That's how I'm going to define quantum causal models. We didn't go that route in the paper. We more so started from a more fundamental idea about, what does it mean for one variable to be a common cause of two other variables, or, variables to be related in a kind of causal structure, and then showed from that basic, more fundamental definition of what this kind of what it means for variables to be related in a causal way, that you can show that from that principle in the classical SEM case, you get deterministic functions and conditional distributions, and the quantum case, you get these unitary maps and what are called channel operators. But what's interesting is in the channel operators, it's like a big matrix, so you can kind of think of it. And on the diagonal of it are just conditional distributions. The off-diagonal points are these kind of variables that tell us about the superposition of the coherence between certain different, states in a given physical system. And so, when we go from the micro to the macro realm, usually this is described by a process called decoherence. It's about losing information to the environment as you kind of go up to different kind of length scales or different physical scales and so forth. And you can show that as this process happens, what that means mathematically is that the off-diagonal terms in these operators go to zero, and you just maintain these diagonal terms, which turns out are exactly just the conditional distributions that we see in standard SEMs. Unitary maps become deterministic maps when we apply these decoherent channels and so forth. And so you get this nice kind of transition between these kind of two formalisms in this specific way. So yeah, it was a lot of fun to kind of work on this problem and try and figure out things in a causal way in the quantum realm.
Recently, after spending a couple of years in industry, you, in a sense, got back to physics, but now not to the micro or quantum level, but rather to the macro level, the level of stars and galaxies and so on. Can you tell us a little bit more about your recent projects, your comeback to physics, and how it relates to causal modeling?
When I left academia, I kind of maintained like an honorary position at University College London, where I was doing a research fellowship before I joined industry. And over time, it kind of built. So I'm now this honorary associate professor, and what that comes with is interacting with students in various doctoral programs in UCL, giving some guest lectures, taking some students into the lab for internships and so forth. And one student that I've been interacting with quite a lot, saw some of the kind of lectures I gave on causal inference and thought, oh, maybe those things would be really important for, the topic of my doctoral thesis, which is all about astronomy and properties of galaxies and how galaxies evolve and all this kind of stuff. Because here, usually when we think about physics, we think about, areas where we don't need causal inference because we have controlled experiments, right? If we can do controlled experiments, we don't need to do causal physics or causal inference. But in cases like astronomy, when we're looking out at the night sky, we can't do these controlled experiments, right? If we want to understand why certain galaxies are the way they are, we can't do this random intervention and so forth and figure out what the consequences are. So causal inference is a great toolkit to try and tease apart these processes and figure out what's causing what and so forth. So I've been working with the student whose name is Sunil Mukesh and his supervisors at UCL, so Offer Lahav and Will Hartley, on a project that apparently is a kind of long-standing project in astronomy. It's all about, what's important for the evolution of galaxies. Is nature or nurture more important? So nature is more like the environment that the galaxies find themselves in, and nurture is more like the internal processes of these galaxies and so forth. And obviously, as in many other cases, like in biology and so forth, these things are entangled together in difficult ways. And it turns out you can use causal inference to try and disentangle these types of things over time and so forth. So one of the kind of main questions we try to address in service of answering at least part of this kind of question was, does the environment that a galaxy finds itself in, does that influence the star formation rate in that galaxy? So general background is there's two generally distinct classes of galaxies, one big red massive galaxies and one kind of, younger blue kind of galaxies. In the blue galaxies, stars form and they're kind of made and so forth, whereas in the red ones, stars generally don't form. And another interesting fact about these is that usually the red galaxies appear together in kind of clusters. So the environment of a red galaxy is different to the environment of a blue galaxy, which is usually on its own and so forth. And so we wanted to understand, does that clustering behavior, does that explain, is that a causal effect for the star formation rate, or is it that this just an association, right? Is it got nothing to do causally? It's just a common cause that explains both kind of phenomena and so forth. So Neil and Will spent many, many long hours going through the astronomy literature and trying to figure out what's the DAG in this case, right? All these different processes, what's causing what? How can we be certain about the causal arrows? They use various kind of techniques to do this, plus lots of domain knowledge from kind of astrophysics. And in the end, they had this beautiful DAG that they had drawn. And then we kind of coupled this with data, simulations and so forth, and then tried to see, okay, could we figure out, looking at the environment of the kind of galaxies and the star formation rate, what are the confounders between these two objects? They found various candidates that when you control them, they what's called deseparate the kind of association. So there's a sufficient adjustment set. Once you control for them, you can be sure that whatever's left after the adjustment is causal effect, assuming our DAG is correct. And from that, they found some interesting stuff, which was, it is the case that actually galaxy suppresses star formation rate, again, assuming the DAG is correct. And so, the more dense one's environment, the less likely it is that they'll kind of form stars in this kind of way, which was kind of cool. But what was really cool is that actually you can, unwind these processes back through time. And you can find that, okay, generally it's the case that the environment suppresses star formation rate, but in the early universe, it turns out actually that it enables star formation rate. So it's really good for star formation rate in the early universe, but then over time it suppresses it and so forth. And this kind of finding about the early universe wasn't known before. So that was kind of cool. Papers we submitted to a journal a few weeks ago, so it should be on the archive soon. But yeah, it was a lot of work kind of getting back to physics and showing that actually causal inference is important for physics, right? There's cases where we can't do controlled experiments, and here we can use these causal tools to try and answer fundamental questions about physical systems, astronomical systems, and so forth.
What's the common denominator for all the activities you've been doing in physics, in science, then going to industry? And we haven't mentioned it so far, but you also write for New Scientists. So you also popularize science. What is the common cause or the common denominator behind all of this?
Yeah, I think I clearly have too much time on my hands doing all these different kinds of things. For me, I mean, there's kind of two things. So there's one is that the thing that like interests me most in all these things is like the questions you can ask. Like interesting questions around why do we have this weird association between quantum systems that are far apart? How do we explain that? Like that's an interesting question to me. The same with this astrophysics kind of stuff. And causal inference is like a really cool area where you get both these, the ability to ask these deep philosophical questions. Like even going back to the ancient Greeks, there's this philosopher called Democritus. He was one of the people, him and his mentor, physically or like devised the idea of an atom before you could even do experiments, right? They said conceptually, if I follow these principles, atoms must exist. So they're really into this kind of foundational knowledge and so forth. So Democritus has this cool saying, which is, I would give the kingdom of Persia if I could discover one true cause. So, it's all about understanding things. Causally is the most important thing in the world. And, from the point of view of philosophy, that's all we should be doing. At least that was his view back in the day. But also causal inference spans, way more practical things at the same time. So there's this cool spectrum between foundational physical things, but also, really useful tools that you can build when you understand what thing is a cause of what other thing and so forth. And for me, this kind of marriage is, what really excites me. When I was 5 or 6, I remember going to primary school, And we're talking about, careers and what job you could have when you grew up and all this kind of stuff. And all I liked doing at the time was building Lego, right? I just would sit for hours and just put the blocks together in various ways and so forth. So I remember asking my parents when I came home that day, I was like, what job could I get where I could just build Lego all day? That's all I wanted to do. And they were like, oh, if you could be an engineer, that's kind of what you could do. So over time, I was really into this practical building things together and so forth. But also, as I grew older, I got more interested in these more foundational questions and drifted away from the practical kind of aspect of these kind of things. But still, I really wanted to do something useful in addition to understanding things or, answering these interesting fundamental questions, or at least trying to. So causal inference was this kind of perfect area where you could marry both these two things, do something applied and practical, while also still some of the time doing things that are kind of foundational and asking interesting questions about the world.
Great. A few weeks ago, we both had an opportunity to speak at the Royal Society in London during the CAI conference. And one thing that I noticed there was that people got really interested in different types of methods that allow us to do causal inference when some of the assumptions are violated. What materials would you recommend to practitioners today for them to get a chance to familiarize themselves with some of those methods that, in your experience, are useful in practice?
Yeah, it's a great question. There are a lot of kind of really good resources out there, both from academic papers to textbooks to notes that are online and so forth. So one of the places that I first kind of got deep into this was I read a paper by Victor Veitch and his collaborator, which had a great title, which is Sense and Sensitivity Analysis, right? A play on the Jane Austen kind of stuff. And so there they had a really kind of clear way for introducing methods to do sensitivity analysis, why it's important, but also, how to illustrate that in a nice graphical way where you could explain how certain you are about certain violations of certain assumptions in a way that's easily understandable by maybe a non-expert or someone who wants to understand what the causal effect is. They don't really understand the mathematical details, but you can show them a nice picture or graph that really explains, okay, should I be confident in these results or not? So I think that paper is really good. And there's kind of lots of interesting other papers. There's a guy called Carlos Canelli, and he has lots of nice papers in a nice package as well. You can kind of use to do these types of sensitivity analyses. And there's, lots of other ones. There's a great one called Equality Constraints and Causal Inference by Pearl and his collaborators. It's all about figuring out, okay, where certain types of assumptions occur in many different causal inference cases. So even in difference, we have to make assumptions that the before and after is the kind of same, or it's the same confounders that are influencing in both cases. And so it's a kind of equality constraint that has to be the same, or has to be equal, and so forth. There's lots of other areas where these equality constraints pop up, and you can show when they're violated in certain ways. You can get sensitivity bounds and all these kind of things, and say, okay, well, if that's violated by this much, how much would my causal effect be violated by? And you can understand then how to propagate these kind of uncertainties about the assumptions to uncertainties about the causal effect estimates. So they're where I would start. And I think there's, a lot of cool other resources out there, just generally about causal techniques that kind of help in understanding these kind of slightly more advanced kind of things.
Great. Before we conclude, I wanted to go back to your personal experiences. What are 2 books that changed your life?
Well, one, actually, going back to the discussion on kind of causal physics that kind of kicked us off earlier on, is this book by this physicist, John Bell. It's called Speakable and Unspeakable in Quantum Physics. And it's all about, it's a collection of his papers and stuff. And there you can kind of see, how he derived his theorem and how you could see him even in the mid-60s thinking along these causal way. Like he drew something that looked kind of like a DAG, even though nobody was drawing DAGs then. So he explained that, you could have these types of associations and they could be explained by a common cause and all that kind of stuff. And the more I learned about this, I was like, this is wild, right? Even before we get to applications in quantum physics, that's interesting, right? This way of formalizing things. So there's a great paper in there called La Nouvelle Cuisine that really spells this out for general audience. It's really cool. So that book was, I think, transformative. What's interesting actually when I think about it, so when I did my master's in Canada in theoretical physics, and I was thinking about Bell's theorem, and I was working with someone there called Rob Speckens, who's big into this kind of marriage between causality and quantum physics. I started a project with him, my master's thesis, and I just finished reading this book by John Bell. And Rob took down a book from a shelf and handed it to me and said, okay, we're going to do something in this area read a few chapters from this and come back to me and we'll chat about specific problems. And the book turned out to be Causality by Pearl. I was like, what is this book? Like, this is wild or whatever. So you can flick to the appendix of Causality, and there's a great kind of transcript of one of Pearl's public lectures, right, explaining all these phenomena, like the do operator and all this kind of stuff. So like once I read that and connected it back to this book by John Bell, like you could draw these DAGs and all this kind of stuff, I was kind of hooked on this kind of interplay between these two areas. So for me, reading those two books had a big effect both on my research in quantum physics, but then also my decision to go and work more on the kind of causal side of things. And it was just interesting that they happened so close together in time and so forth. So yeah, so for me, it would be those two.
What would be your message to the causal community?
When I first kind of left academia and kind of, took this plunge into industry, I really felt that we could use these causal tools to do something useful. And I couldn't really find a lot of examples apart from, like understanding the impact of various policies and so forth and kind of econometrics, even though at that point I hadn't been exposed to a lot of these papers. But like in big industrial companies, I hadn't found places where we were using these tools in a really interesting way to actually both make decisions, but also drive decisions. So not just do retrospective analyses to understand, okay, was this product launch, did it have the impact we wanted it to have, but how to build a new product using causal inference, right? To me, this seemed like a really cool thing to kind of do and something that we should devote time to because it's more trustworthy and all these kind of things. But no one really had done it at that point. At least I hadn't come across anyone who had done it. And so I really think we have a lot to offer. And we should go out and try and find some interesting problems where we can apply these tools, because I think there's a lot of areas that are kind of crying out for them beyond quantifying the effects of interventions in certain situations. I think we can do more. And yeah, I really feel like we should try hard to find these kind of problems and start kind of working on them to really show the usefulness of these tools in a broad spectrum of kind of ways. But I think as well, we have these two camps, like the potential outcomes framework, the SEM framework and stuff, and they're more similar than they're not. And I think both frameworks have useful things to teach the other framework. So I think we should all work together a little bit more and kind of use conceptual advances from both to push both forward. So I think we should go out and find interesting problems and kind of push the toolkits we have to make them better and make them more applicable to these real world problems.
Well, what's next for you?
So at Spotify, we've been having a lot of kind of success recently with like the types of projects we're working on and like the areas in which we're applying causal inference beyond just, as I said before, what was the impact of that product launch or that new feature or whatever, to really drive actions and so forth. So a lot of these are kind of at a late stage now. So we're, final testing and so forth. And so I'm really hoping that they kind of see the light of day where I can talk about them quite a lot publicly. So I think in the next few months that'll happen. And, if you follow me on Twitter, I'll just be talking about those all the time. So I apologize in advance if they hopefully turn out to be successful. So it's really driving those, but also, really kind of figuring out the best way to use causal inference to, address interesting kind of questions, right? Like what I left this startup that was, involved in kind of healthcare stuff because, after the initial success we had with this causal approach to diagnosis, we had lots of kind of models that were all about, how to personalize treatments to given users and all this kind of stuff. And, rightly so, we couldn't just launch these products in the same way a tech company would launch them, right? Because there are kind of ethical repercussions to doing these things. You need a lot of, certificates and to pass all these kind of things and, recommend these types of things to users. And so, part of the reason why it came to Spotify is that a lot of the problems that we were dealing with at Spotify at a conceptual level, at least, are very similar, right? Recommendations are kind of like treatments on a user, right? You want to find a song that will cause a user to enjoy it, right? The same way you want to find the treatment to cause a user's symptoms to decrease and so forth. And my hope is that if we could show we could use causal inference in this really kind of novel way in this, slightly lower stakes setup, right? If you choose a bad song, it's not the end of the world. If you choose a bad treatment, maybe it is. So we really want to show that it's useful, right? That you can do these things in a way beyond just quantifying, the impact of a policy and so forth. And we're like almost there at Spotify. We're almost launching products that are powered by causal inference, and hopefully that will expand in the future. But I really think the next horizon is like trying to use techniques from causal representation learning to start doing this. Like in almost all big tech companies, we learn embeddings of our users, of our products, and all these kind of things that describe certain products being similar, certain users being similar, and so forth. And the standard way that that's done is using co-occurrence data. So that is to say, just correlations between these things. Certain users did the same type of action, so they're close together in this embedding space in this kind of word to vec, sequential transformer style way. But if we're learning embeddings based on correlation and then using them as inputs to a recommendation engine, which is all about finding a treatment to cause an outcome or finding a piece of content to recommend to cause enjoyment or whatever, but we're using correlations to power that, it seems like the wrong thing to do. Right. So it feels like we could do better by learning a causal representation of users that, find the factors or the latent factors underlying why users are similar or why they enjoyed a certain piece of content. And that could help us improve things. And, if we could demonstrate that at a place like Spotify, right, that we could use these things and it actually works, then perhaps we could use them in other high stakes domain like medicine or, various other areas. And so that's what I'm, hoping to push towards in the next few years.
That sounds really great. Where can people find you and connect with you?
So I'm on X or Twitter every now and again, even though it's changing quite rapidly over the last few years. I think my handle started when I was in quantum physics, so I'm at Quantum Kieran, a hangover from a bygone age. On LinkedIn as well, you can send me an email either to my Spotify account or my UCL account. I kind of check both regularly. There, you can find them on my website and so forth. So if anyone has any questions, please send me an email. Always happy to chat about all things causal.
Great, Kieran. Thank you so much. It was a pleasure.
Thanks, Alex. Yeah, great chatting to you.